Section 4. Simulation Methods. In a simulation method, different scenarios for the portfolio value at the target date are simulated. These scenarios can be generated in a random fashion, or from historical data, or in other systematic ways. The simulated scenarios are then used to generate a distribution of portfolio profit and loss values from which the portfolio VAR is read off. These simulation methods are powerful tools for estimating VAR and can handle any type of portfolios, however complex or exotic. When compared to delta normal methods, the strength of simulation methods lies in its capacity of handling a wide variety of financial assets, as well as risks of different types or natures, including risks with nonlinear positions, prices dependent on more than one stochastic variable, path-dependent pricing, for example, Asian options, time variation in parameters, for example, in volatilities and correlation, non-normal distribution, for example, fat tails or skewness, complex derivatives which do not have analytical solutions, for example, American options. Now let's first introduce the Monte Carlo simulation method for estimating VAR. Monte Carlo methods take random draws from a prescribed stochastic process for each of the risk factors. For example, it could be the geometric Brownian motion for a stock price. Through random number generation and sampling from the relevant distribution, a very large set of scenarios for the risk factors is derived. These scenarios are then applied to the portfolio, whose value is dependent on the simulated risk factors. The resultant set of portfolio value changes is then sorted to yield the required portfolio VAR. Here, we will illustrate the Monte Carlo simulation method by estimating the VAR of a European option whose underlying asset price follows geometric Brownian motion. Suppose the current option value is Vt. Under the geometric Brownian motion, the underlying asset price at the end of the risk horizon h is given by the following expression, where epsilon is a standard normal random variable, mu is the drift rate, and sigma is the volatility. First, generate a pseudo-random sequence of n values of epsilon, and by substituting which into the above formula, we get n values of st plus h. Then, for each value of st plus h, compute the new option value vt plus h at the risk horizon. Finally, VAR is obtained via the relevant quantile of the resultant discrete distribution of delta v, that is, the change in the option value over the time horizon h. Next, we'll talk about the historical simulation approach. It is a non-parametric method and makes no assumption about the distribution of risk factors' returns. Hence, it is robust. The method applies current portfolio weights to a time series of historical asset returns, denoted by RIK, with superscript h, meaning the return is calculated using the historical data. Here, I refers to the ith asset or risk factor, and k refers to the case observation. Each scenario k is drawn from the history of t observations. VAR is then obtained from the entire distribution of the hypothetical portfolio returns, with each historical scenario assigned a certain weight. Here are the steps to be taken for estimating VAR using the historical simulation method. First, obtain percentage price change series for every asset or risk factor over the same period as the required VAR horizon. Then, apply these price changes to the portfolio, thus generating a historical series of portfolio value changes. Next, sort the series of portfolio value changes. And finally, use the assigned weight of each portfolio change to obtain a corresponding confidence level that loss will not exceed that particular portfolio change. Note that the VAR is the portfolio value change corresponding to the required confidence level. Interpolation might be necessary in this step. Let's take a look at the following example. Consider a portfolio of 3 assets with values $2 million, $3 million, and $1 million respectively. Suppose a set of 20 historical price change series for these assets are obtained. First, we obtain the corresponding portfolio value changes. For example, for the case when k equals to 1, the asset's price percentage changes are 0.06, 1.1, and minus 0.35 respectively. With the given values invested in each of these assets, we can get their corresponding dollar changes. They are $1,200, $33,000, and minus $3,500. Summing them up, we get the portfolio change of $30,700. Then, we sort the portfolio value changes in the ascending order as follows. Suppose a uniformly weighted scheme is used for portfolio changes, with each portfolio change carries a weight of 0.05. We obtain a confidence level accordingly. Therefore, the portfolio's absolute VAR at 95% confidence level is $99,000.